Hello, everyone. I hope you can hear me and see me. Hi. If you can hear me, kindly type a yes in the chat box. Thank you, Daniel. Thank you, Tom. I can see Tom and Manpreet are already on call. I'm so excited that you're here. We are excited to host you. So before we start, I want maybe to take sort of record. We've had two more sessions early in the day, East African time. We had one at 11 a.m. and another session at 3 p.m. So I want to know how many of us who are in this call right now were here at 11 a.m. and also at 3 p.m. You can type a yes in the chat box. Thank you, Maureen. You were here at 3. Thank you for joining in again. Who else was here in the previous sessions? And you too, you're here at 11. Thank you for coming. Kuria, thank you for coming again. We are so pleased to have you. Who else was here? 11, Tebogo, thank you for coming. Who else came for the previous sessions? Oh, Victor, all sessions. Thank you for supporting this community and for joining in all the sessions. We appreciate. Who else was here? If no one else, I guess we shall start then. I didn't introduce myself. My name is Mabel Karani. I'm a student at Jomo Kenyatta University of Agriculture and Technology. I'm taking telecommunication and information engineering, and I'm happy to be here to host this event. It has been a really successful day. We had amazing turn-up, and we are excited. We are really happy to host Tom and Manpreet. So I guess we shall get started. I shall invite Tom first. Or maybe you can introduce yourself first before you start. So we'll start with Tom.
Sure, I'm happy to, and I'm glad to be here. And let me warn my family that I'm presenting. Okay, great. And oh, Mabel, just so I'm careful, how long do I need to limit my talk to?
Okay, you can first introduce yourself, then Manpreet will introduce herself, then maybe we can have maybe 30 minutes.
Okay,
then
that sounds great.
Minutes, then we'll have a Q&A later.
Very good.
Okay.
All right, very good. Well, my name's Tom, and I'm older than dirt. And no, seriously, I was born and raised in Dallas, Texas. And then I went off to the University of Texas in Austin. I worked for my nation's naval nuclear power program for about 4 years. And then I returned to grad school because there were some things I really wanted to master, which was predictive modeling, but using physics. And a lot of times when engineers and physicists are doing predictive modeling, they have to do what's called empirical modeling. And so that's a very, it is essentially data science type work, but for engineering. And over the years, I continued to love to code. And when Python came out, and when I discovered Python, it was about 20 plus years ago, and I fell in love with it. I felt like I was set free, and I kept improving my automation skills. And at a certain point, I realized I just didn't feel like I was taking my career in the best direction. I met with a friend, and he said, "Well, Tom, you're a data scientist." And I said, "Yeah, I guess I'd say that." He said, "Well, Tom, do you know how hot that field is?" And I said, "Scott, I know less about current events in the world than anyone else I know." So he caught me up, and then I realized I couldn't rely on my existing network to get into data science. So I worked hard to build an online presence, show what I could do, and then it was actually not too long ago I got my first role as a data scientist, and but I'd been doing data science for years, and I absolutely love it, and I love mentoring new people coming into the field. And I will share my screen with y'all and get into my presentation. And what's nice about this presentation, it's an overview of the basics of what we would call machine learning, But machine learning, we've had a lot of great, what we would call inventions in the space of machine learning. But this talks more about how to make sure you can do it in a high-speed way without forgetting anything. Let me give you an example. Carl Benz created or invented the first automobile, but it was Henry Ford who taught us how to make them more quickly. And that's what I'm trying to get at by what I'm saying in this talk. And this talk really has to do with understanding methodologies and the basics. And this is something I wrote a while back. I love to share it because it's a sum of learning that I've encountered. Many great mentors in many forums that I've encountered, they all say one powerfully reoccurring thing, and that is the greatest practitioners, that is the people that actually do something in any field, take the time to master the basics. The basics are the foundation of any great art in life. And I'm including our data science arts in that. Masters literally practice the basics tens of thousands of times. And I'm all for the latest cool tools and techniques, but they will crumble as a house with a poor foundation if not built on good basics. And this is certainly true about machine learning. Now, this is a nonlinear summary of my entire talk. And I expect, if you've never seen this talk before, if you've never seen this diagram before, this would seem overwhelming. And please don't let it overwhelm you. Or let me put it this way, if it's overwhelming you, it's okay. But by the time we go back, when we come back to this at the end, you'll go, oh, okay. If you've ever had that experience of looking in a commercial airplane cockpit and seeing all the gauges and controls, that can seem overwhelming until you've gone through all that training and you get to know each thing. This is not as bad as that, I promise you. But we'll go through all of this, and we'll go through it piece by piece, and then we'll present it again at the end. But we're really, the reason I show these fruit pictures is we're trying to get the fruit out of the data. We're trying to really pick the good data so we can do a good process. That's really what this comes down to. All right. So then, at the highest level, though, we have a pipeline we're developing, and we have features. And really, features are just inputs. But we have to remember that the data that we're getting as features, it's really from a population, and we've sampled this population. So we need to reduce those features down to the essentials for what we want to predict, because we're just going to engineer, and then we add some features, we engineer them, we kind of create them for possible additional needs, and I'll show that. But our outputs are our labels right here. And then the models, we just work through several models to find the best one. And then we have the humans still involved overwatching the process, because as our data assets grow, that is, as we have new data coming in, the size of our data will grow, and that can cause the output from our models to drift. All right, now when we say models, we're saying a type of math, a math machine, that takes our features and helps us predict our labels. But we have to have some known outputs for given inputs in order to train that model. We'll go over that a little more right here. So we have features as inputs, then we run those features through the model. I like to call them math machines. And then we make a prediction. Now, the first predictions are really bad, but we take that error, and between the prediction and the labels, and then we feed that back, and we go through this very clever mathematical process to update the model parameters. And after we've gone through enough of these cycles, we get, hopefully, if we've set everything up well, we get an accurate model. All right. Now, we've got to feed data into these models to train them, but sometimes we have missing values. And so this is something we want to deal with. And there's different ways to deal with missing values. If you have too many missing values, you're just going to have to delete because it's a travesty. That feature may have been very important, but if there's way too many values missing, you're just going to have to delete. But you can be clever about the way you delete, and that's what this is going through. Now, the other thing you can do is imputation. Well, all that is saying there's fancy ways, depending on what type of problem you're working on, to fill in those missing values based on the other data you have among your features. And in the most clever cases, we're actually using features to predict other features, like like the example I just showed previously. We create a modeling situation to predict the missing values. And when that is done wisely, it's very powerful and usually much better than just putting in zeros or averages. But sometimes, depending on the problem, you'll use mean, median, mode, random sample stuff. Sometimes it's easy to just do linear interpolation, which would be a form of modeling. But sometimes we actually get down into linear or logistic regression, meaning the models are doing either a type of classification or a type of continuous prediction. So there are some really good ways to deal with missing values. And then some of our data is just not clean. Well, how do we deal with that? Well, if you haven't heard this, I'll be the first to break it to you. Most of data science work is not sexy. But if you're a true data scientist, you don't mind doing it because you realize goodness in equals goodness out. Now, I'm trying to start saying it that way instead of garbage in equals garbage out. But we're aiming for the goodness. And we're looking for just data that needs to be clean. So sometimes we have a lack of data or an excess of data. This is one of the ways we can clean. Sometimes we have outliers or inconsistencies, and that means we need to go investigate those things. Sometimes we see strange patterns, requires further investigation. But there's always ways, almost always ways to find errors and missing data and deal with these outliers. But if we can't, there's other techniques to deal with those outliers that we're going to go through here shortly. Now, once we've got it cleaned, let's remember something else. All machine learning problems are math problems, and math problems deal with numbers. So if we get text in our data sets, that's not the end of the world. We can do different types of word to math encoding or word to number encoding. So the most common type is, let's say we had 3 colors here. Well, I can just say, oh, I'll just have a column in my data set now for each color instead of this color column. And when it's red, I'll give a 1. When it's blue, I'll give a 1 for blue and a 0 otherwise for red and blue. And when it's green, I'll give a 1 there. But let me point something out. If red and blue are both 0, we can eliminate the green column or one of these 2 other columns. If we had, in other words, in colors, we only need n-1 encodings. And by the way, making sure that you do n-1 encodings when you're using one-hot encoding is a way to avoid mathematical challenges. Let me just put it that way. Another type of encoding is ordinal encoding. So let's say we went from bad to poor to okay to good to excellent. Well, we can just make bad 0, poor 1, okay 2, good 3, and excellent 4. And so that's an example of ordinal encoding. But this is one of my favorites. Let's say you had a big group of documents, and I've done this in my work, and it's been hugely valuable. Well, let's say I've got words in all of those documents. I collect the different words, and then I explain the occurrence rate of each of those words in each of these documents. Now I've actually encoded each of these documents would be a column, and each of these rows would be a word. I can say the rate of occurrence of these words in those documents. Now, some of you that may have been further along in your education might think, well, wouldn't you encode this into a big hyperspace? And you would. In fact, this is bigger than those word embeddings or word to vector type routines. It keeps it very open and makes it dynamic. Thanks to routines like sparse matrices in Python, we can go really fast with stuff like this. But if you were aware of word to vector or glove, you're absolutely right. We do an unsupervised learning method to basically encode these into a hyperspace with a number of dimensions of our choosing. So there's all sorts of ways to turn text into math, and it's gotten even better lately with transformers, the latest form of deep learning architecture that's just breaking all sorts of previous boundaries in language processing. Well, then, what would we next need to do to these features? Well, what we frequently want to do is normalize them. And what we're trying to say, for example, is let's say you're doing the modeling for body mass index. Now, this means your height to your weight. And we would expect for men, as their height goes up, their weight goes up. And for women, as their height goes up, their weight goes up. But sometimes some of us eat too much, and I can confess to doing that sometimes. But if we really, when we're doing the modeling, we want to put all of these variables on a level playing field. So we use various types of scaling to put them all in a similar range so that when we do the modeling and we get model parameters, they can tell us the importance of those various features. So that's a big reason to scale. Put all the features on a level playing field. So there's many more than this, but we've got min-max, standard, like we're treating it like a Gaussian distribution, the quantile, which you've seen with box and whiskers plots, if you've seen those, the power, and the unit vector. And all of them can be good. Some of them are more appropriate to certain problems than others. Okay, now we also want to reduce the features. Not, what I mean is, we want to reduce the number of features to the set of features that are most necessary. If we have features that aren't really helping us with our predictions, we get rid of them. And one of the reasons we have to get rid of certain features is co-linearity. Imagine two features are really doing the same job. So we want to get rid of those, but how do we go about that? Well, when you see two features that are not collinear, when you plot them against each other, it'll look something like this. But when they have a strong relation to each other, a strong correlation, you'll see something like this. And in that case, you would want to use only one of these, and then what you could do later is just use this same relation to relate those two. But what causes collinearity among the features? Well, redundancy, as I've already pointed out. But why is it bad? It reduces the accuracy of the model weights. And also, the sources are inadequate data collection or an overdefined model. But how do you identify it? With a correlation matrix. Basically, you see these two plots. We do all of these in either a matrix, these plots, or we show their correlation strength numerically. And then there's another type of way that's the variance inflation factor. But how do we deal with it? Well, we can collect more data, we can improve the sampling method, we can reduce the noise, which is an item I haven't put here, and we retain one of the collinear variables, just one of them. Okay, but what are some other ways to reduce them? I mean, maybe we care about correlation among features to reduce collinearity, but we also care about the correlation of these features to the label. And so if some of these features are not very useful to our predictions, well, we can take a simple model and loop through it and use different methods for doing that and find out the correlation strength and just reduce those that aren't adding much value to the prediction. Now, here are some examples of what we mean by correlation. Here's a perfect positive correlation and a perfect negative correlation. And here's no correlation and everything in between with these other four. So, but for each of these, we get a correlation value. And that's how we can create these numerical correlation matrices. And these are the two most common types of looking for correlation strength. Excuse me, the two most common calculation methods or algorithms. Now, there's a powerful method we use in linear and logistic regression called lasso. And so if we're doing regression or a continuous output type problem, we could use linear regression and lasso together, and lasso will drive the feature weight, the weights on the features in the models to 0 for those that aren't very important. And a super powerful method. It doesn't use an Euclidean norm like a hypotenuse, if you're familiar with triangles. It uses actually the distance going through each leg. And there is also another form of, and by the way, lasso and the other thing that we use that's like lasso called ridge, they are ways to deal with outliers in our models too, but hopefully we can find ways to deal with them before this stage. But when you see the model weights that came very close to zero or are essentially 0, that's an indication of features you can eliminate from your model. Oh, I should go back up. Also, we're using metrics when we're looking for these features that we can eliminate. We're using metrics to tell us the accuracy and the generalization of the model, but also the parsimony. And parsimony is just a fancy way of the KISS principle, keep it simple, stupid. In other words, we just want the basic set of features that will do the job. We don't want additional features that will just cloud our judgment or are not adding value to the predictive accuracy and would tend to hurt the generalization. Okay, finally though, once we have that best set of features or that best set of inputs, there's times we need to engineer new features. Well, why would we need to do that? Well, here's a very simple problem where we have no feature engineering. And so I've used a model to predict the best straight line that can go through this. But what if I add an engineered feature of x squared? And I'm not even actually sending x into the model, or I'm sending it in and I find that it's not giving much weight to x, or I use lasso and it drives the weight for x to 0. Now I know that this model only needed an x squared. And so that's an example of using feature engineering and getting better predictive ability. Now, some of you may have read that when you use deep neural networks, they automate the feature engineering. And what we still want to point out is, okay, that's great, but understand that deep neural networks require a lot of data for good training. So reduction of features still helps. And if you figure out some engineered features ahead of time, you can make a simpler deep neural network. So it still pays to reduce dimensions and do what feature engineering you can. But for those extra complicated engineered features, I think it's very smart to let the deep neural network figure those out. So this is the whole thing about features, and they require much attention. But if you give much attention to them, not only will they help you do good predictive modeling, but what you've learned from your study in getting the features to their best state, you can communicate that back to your greater organizational partners, and they can use that information for their decisions in running the organization. Now you're helping them be data-driven even before you've given them the model predictions. Okay, the labels, the outputs. In rare cases, we can even engineer the labels to help simplify the modeling. But do we scale the labels? I've never thought to do this, but like all good data scientists, remain open and explore possibilities. That could be a useful thing. Okay, now let's get into the models. Whew. How do we train them? Well, we've got to randomize our data. That's why we call this shuffling. We split it into train and test. And when we get even more thorough, we make several folds of train and test. And I'll illustrate that in a minute. But it's making sure that every part of the data has been used to train the model, and every part of the model's been used to test, every part of the data has been used to test the model. And then we also want to explore hyperparameters in the models. That this bullet shouldn't be in this group, sorry for that. Now, the metrics. When we say generalization, all we're trying to say is, hey, we're training on data we have in hand, but when future data comes in and we need to predict that label, we don't want our model to be overtrained so it goes crazy. So we make sure the model will generalize well, and that's yet another reason we train with this cross-fold validation, to make sure it's a good prediction across all folds, not just looking for the most accurate model possible. And one of the great ways to achieve good generalization is with parsimony. But there's also a motivation to automate all of this. And so we basically let the automation choose our model. Now these, real quick, these are the types of machine learning, supervised machine learning, where we have labels. Unsupervised learning is when we don't have labels, but we can still do some very powerful techniques there. And there's another branch above here when we think of just data science in general, reinforced learning, which is quite different than machine learning, but beyond the scope of this presentation. And this is an example of cross-fold validation where each part of the data gets a chance to be the test part of the data, meaning we train the model with this. We've got known features and labels, and then we use this part of the data, we use the features in the test part to predict the labels and see how close they are to the labels. And again, we want not just highest accuracy, we want good accuracy across all these folds, but good generalization too. That would mean that each of these are accurate, but this distribution of accuracy is very tight. There's almost no standard deviation between those, or as little as possible. But then again, as more data comes in, if you understand the central limit theorem, the characteristics of that data can change. And we trained on a smaller set. Now that we have a bigger set, we should be open to retraining the models, looking for models that work better on the increased data, etc. So we're constantly watching the process, even if we completely automate it. And now, hopefully, when you see this whole thing, it's not as overwhelming. So, any questions? And I'll leave this slide up because it's a good summary. Yes, I will share These are publicly available, and I'll make sure you guys can get to them. All right.
Okay, I think we'll go to Manpreet first, then we'll have a joint Q&A at the end.
Okay. Sounds good. I will stop sharing.
Yes, hi Manpreet. You're free to present. You can introduce yourself, then go ahead.
Hi everyone, this is Manpreet from India. I currently work as a data engineer, and thank you so much for inviting me to your session today. So, from the previous talks by Thom, you know what's feature engineering, how to train model, and how to do different things. But how do you get the data, and what's the true essence of being a data scientist, who is actually called a data scientist? So I'll be talking about few points, not presenting but just speaking out few points that I have in mind regarding the data, because data is the most important thing you need to process all the other things that you learned in the previous talk. So moving ahead, so one important thing I feel is you should know your data. Um, if you want to build a sentimental analysis, you should know that you have some text that gives you some sentiments out of it. If you do not have that data, so how would you build or train or make or do feature engineering or clean your model or do anything on that? So the first very important aspect of a data scientist is that he knows or she knows its data very carefully. It's very important. Like, for suppose you are starting up your own business and you want to build a project, or you have some business idea or product to build on, but if you don't have that correct data in your mindset, how should it look, how should we store it, and what should be it all about, I guess it doesn't make any sense moving ahead further in the next steps of visualizing or projecting it to the further steps. The next thing is the data scientist should know is why are they using that data, because if you don't know about your project and why did you take that data for, so it's very important. Suppose I want to do a customer I did a customer reviews, and now I want to see how my customers have rated my product into. So I need to out of this project, it's giving me how my product is being sold to particular customers and how they're reacting to it. So through feedbacks, I'll know that these features of my products are not good. um, these are the features that are liked by the customers, and they have given ratings to my products like around 3.2. So how this helps to me to improve my product further ahead. So why I need that data is to improve on myself. If I don't have that data, I would never know how I'm doing in the market, how is it being sold, how is it there. So it's very important that you know about your data well. Next thing is how to use that data. And sometimes you would get very overwhelmed when you see data sets with so huge data sets and so many features and columns. But if you don't know how to use it, how will you actually make a good use of it to serve your product or something? Sometimes when we are at work, we have huge list of data, and we get so excited. Oh, we can do this and this and this, but finally we end up doing nothing out of it because we never had a direction of how we'll be using it. So having a roadmap to know what categories and how you can interlink different columns and data to how you can interlink different rows and columns to get a particular data out of it. It's very, very important. That makes you a very good observant as well, to know that, okay, suppose you have the same customer review thing. What all you can do is you can make reviews classification, so you can have even that people don't cannot afford your product because it's very costly. So you can create keywords or topics to put your reviews into different topics. So that helps you even to realize, oh, most of the people don't like my product is also because it's into affordability category. They can't afford so much, so they usually use the free version. Or some companies are providing these data. Some companies are giving subscription of our data to their employees, so they are using it. Else they would not use it. So there are various things you can just do with reviews, not just sentimental analysis, but even classification and grouping them. And even if you have timestamps, you can see, okay, when the product was launched, yeah, people used to have this view on it, and now with time people have so what view on it. So with time things changes, so it's very important for you to know the use of your data and what purpose is it going to serve it. Now once that you know why you're using that data and how you're going to use it, but what purpose or what product are you going to build out of it that could give a purpose. Now when you interact with people, you would see, okay, I'm building an AI company, I have this AI company, but they don't have a clear idea in mind that how will these products or the data set they are trying to build is how would that serve to the community, or what data or how that data set is going to be used to make a good product that can help the community. So these are very important points of being a good data scientist. I would say, yes, you do need skills. You do need a lot of things, but if you are someone who can have these skills also, that impresses your interviewer as well, because you can explain them about a product which they might be building and you had read about it, and you can tell, oh, if I read about this your products and I did some reviews classification, I got to know about this, and I think if we can improve on this, this could help the customer. So you have a good point to say in the interview as well, because now you know what is your data and how you're going to use it to your own purpose. So I think these are all very important essence of being a data scientist. I would like Thom to know what are his views on this.
Well, I can't say enough about, as you're going through the process, guys, and studying your data, analyzing it, this is stuff you want to take the opportunity to teach the whole organization, especially those that commissioned you to do your data science work. Even if you're doing your own data science work for an organization, you want to give frequent feedback on your learning, because I think it's interesting, Manpreet. We spend, like we said, 80% of our time getting the data ready. But
yeah,
now Gaith and I, and even Greg, we're starting to realize, oh, that's 80% of the value of what we could communicate back to the organization too. It's not to say that we don't want to predict, but, and by the way, there's several other sciences or domains that we apply predictive modeling to that don't really lend themselves to learning the value from the data, but at least in a business or most typical organizational applications, we need to be teaching our companions in the greater organization the value we're seeing in the data. And it's not like we're asking them to become data science experts, or they should ask us to become business or domain experts. It's that we're building a knowledge bridge where they understand enough about what we do, and we understand enough about what they do to make sure that we're giving each other the most important information. Did that help, Manpreet?
Yeah. Also, because you work into the data team, you have access to all the data, and you can eventually come up and say to, like, suppose a marketing team, we usually get this data, and when we can give you this insights, it can help you market your product more and get you more customers, and help the business team as well to know, when you launch products on weekends or something, people react to it more, or your posts or campaigns during this time are making good sales, so maybe do this more often. So if you know your data well, you can serve it to other people as well, and it can help you generate a lot of profit for the organization you're working for, and even improve your skills. Like, explaining data to different people who are not in tech is also a very important skill that one should have, I guess.
Yes.
Yeah. That's all for my talk. It was short, crisp, and informative from what I've learned working for 1 year now. Almost 1 year now, but yeah.
Thank you. Thank you so much, Manpreet. Thank you, Tom, for the amazing session that you've shared with us. It has been really productive, very, very productive. The main things that you've talked about, but Manpreet and both of you have talked about, is how you should know your data, which is a very important skill. And you said if you know your data, you can serve your organization well. So you mentioned about knowing your data, how to use your data. And Tom also mentioned and insisted that you spent 70 to 80% of your time getting your data ready. So it means you should be in a point of understanding it well so that you can get feedback from people. Whatever you tell
Also, like, I'll add here, when you do
Okay.
80% of work, don't
Uh-huh.
have that thing that you're doing it through Python scripts. It's also that you're doing that work manually at times of
Yeah.
getting and classifying data or cleaning that data. Like, out of that, 40% is you doing manually and 40% is you're doing through scripts.
Okay. Thank you. Thank you for that. Now I think we can head to the Q&A section. I see some people had raised their questions here, starting from Natasha. Tom, can you kindly take us through the questions?
Yes. Oh, I see one up there. I'm sorry, I missed that. Actually, just thought of a question. Must all problems pass through a machine learning process for prediction? And if not, how can you tell that a particular problem would not benefit from machine learning solution? Well, this is an excellent question. In fact, I'm glad you asked it, because it's something Manpreet and I both would have wanted to emphasize. A lot of times, the data visualization is enough. If you're just visualizing the data and you're letting the data tell a story, that's super awesome. It's super valuable for your organization. So what do we mean by this? If Manpreet and I were doing a machine learning project together, we would go through a lot of visualizations, and we might even automate a dashboard to visualize things. But we might learn from that, hey, this is valuable enough. We need to keep developing these visualizations and updating them frequently for the organization. We don't really need machine learning predictions yet. But actually, to do your best machine learning modeling work, you want to go through that level of visualization. So you should be developing it anyway, especially if in a situation where the data continues to flow in. I hope that helped. Let me look for the next question.
Also adding to this, that's why people do ETA analysis, to know that if it's even relevant to move forward. And you can, if you have time and you can do is for like 6 months, you can create a process of which you did initially manually and then get data for like 6 months. That would be huge data set now. And now you can do machine learning things, because with 1,000 rows of data, you wouldn't get something out of it.
Exactly. And another important point, be sure to become friends with the data. Don't interrogate it to death. You're looking for the story it tells, not trying to force it to tell you a story you want to hear. Now, the next question was, where would you advise a newbie to machine learning to start their machine learning curve? Definitely start with the basics that we showed in this presentation, but on linear and logistic regression. If you get very good at linear and logistic regression and know how to apply lasso and ridge, these are basic things to deal with outliers and finding model weights that should go to 0, techniques that help you generalize your predictions. If you get good at those and really try to understand those concepts, you have just prepared yourself in the best way possible for learning deep learning. Because deep learning, or artificial neural networks, are built on the foundations, more like they are the cells of deep neural networks, linear and logistic regression. So, and you also want to understand the peculiarities of gradient descent, because while you can solve a lot of problems with closed form solutions with least squares using for linear regression, for logistic regression, you will almost, I think you always have to use gradient descent. So understanding the peculiar challenges in gradient descent and how certain learning rates and principles, well, that's the basics. You start with linear and logistic regression. Now you may think, seems like for the basics, I should know a little more. Yes. Once you've mastered those two, and by the way, David Langer and I are friends, he would have encouraged you to start with decision trees and random forests. But he and I will not argue on the fact that those are the basics. Linear and logistic regression, decision trees and random forests. You understand how to apply those very well and use that machine learning pipeline we went over. Those are the basics. Learn those really well, and you, like I said at the beginning of the talk, to become a master those basics. I hope that helped.
Yeah, but they might be also asking about the courses. What courses?
Really, there's new courses.
I remember Krutis talk. You like this, I like this. It depends.
It depends. So there's new courses coming out all the time. The courses that have been out for a while that are on Udemy or whatever, but really, there's a lot of free good courses on Udemy and YouTube, and just you've got to find an instructor that you connect with. Sometimes I might connect with an instructor better to this one, and you connect better to this one. So it's a bit of a trial and error, but it's also good to learn from multiple references. Let's say you have your main curriculum and you're going through it, but you hit a point you're confused on. It's really valuable to branch out and go study some other references on that specific item. And then once you understand it, get back on your main curriculum again. If you hit another problem, do the same thing. Look at multiple references. I find that usually interrupts your brain's ruts enough to get you going again. I hope that helped. Okay, I'm looking through. Manpreet, do you see any other questions we haven't covered? And thank you
it's all good.
Thanks for the praise, guys. We have a passion to help everyone, and we're helped by you too, by the way. Okay, great.
Yeah, and I think Thom never knew that I had a talk today.
No, I knew. I just was a little confused if we were speaking together or not, which we could have done. Yeah.
But we eventually did that.
We're always happy to visit with you guys, just so you know. Yeah. And by the way, If you've not connected with us on LinkedIn, let me get my profile. Manpreet, you put your profile in here too. Please connect with us on LinkedIn, and then let us know. By the way, we consider all of East Africa part of our group, which is Integrated Machine Learning and AI. And then Manpreet has her own YouTube channel, which is AI for AIM. But what's AIM? Go in and tell them what AIM stands for.
Artificial Intelligence and Machine Learning, AIM Learning.
Excellent. And but when you connect with either of us on LinkedIn, we can add you to our integrated Slack group, which means once you're in our Slack group, you'll get invitations to our Saturday mentoring sessions, but you can also come to any of the things that we do during the week meeting-wise, and you can experience the richness of our past recordings for sessions. We're having a bi-weekly tech time chat that I'm leading, but Ugo from Nigeria, who's a member of our family, is going to be starting a Python class soon, and there's going to be a mixture of experts, including me and Dennis Rothman and Kuyen Tran, and I'm hoping Manpreet will jump in and teach some sessions. I'm sure Gaith will too. But we just love to have y'all to be part of our overall family. And we even have a class. It goes slow, but we're covering what I just covered in greater detail once a week on my Saturday mornings. The recap of the talk, Amal, I don't think we have the time to do a big, thorough recap, but it was basically showing the basic methodologies you should go through when you're doing a machine learning project. That's all it was really about. And again, I will let Mbaabu know. I hope I'm saying your name right, brother.
Mabel.
Thank you. Oh no, I meant not Mabel. I can say
Harun.
your name.
Harun. Okay. Yes. Harun.
Mbaabu. I think it's anyway. I'll make sure you guys have the links to the slide. And in fact, I did. I was busy over here looking at his post about what we were doing just now, and I'll add a link to the slides in that post as well. And then, yeah, we hope you'll all want to become part. Manpreet's doing something to help streamline the process to allow new people to come in so that they can just join on their own. But it's a link that needs to refresh.
Someone is still pending me to send a message.
Yes, we will work on that. Okay, Vertex tool to train my model. By the way, yes, I'm going to share the slides, Deshaun. I am a very tools agnostic person, meaning if the world made Python illegal, I would just say, okay, I'll go get better at R now, or I'll go learn Julia. I don't even know what Vertex is, but please look at different tools and think which one would be the best for you. I can say this. Python is powerful because it can do so many things even outside of data science. If you start with R, it's great. I'm not discouraging it, but there's not as broad of a range of stuff that you can do with R, but people that know both well, they tend to be very agnostic between the two. People that know one or the other better, one better than the other, they tend to push the one they know better. So, but I will tell you this, those that know them equally well, they'll say, oh yeah, Python can do broader stuff. That's the main advantage. And so if you learn Python and people are being very, I don't like it when hiring people are, concerned that, oh, we want you to be a Python person. You're probably gonna, when they are being that way and you have to take a job with an employer that's being that way, Python's probably gonna be more marketable, but R is awesome. I'm not ever going to badmouth it. How can one join the Data Science East Africa? That is a question for Mabel. And yeah, the slides will be shared. Once I get the link ready, I'll share them Harun's post. Forgive me, Harun. I don't know if Harun is your last name or your first name. I get confused sometimes from when I see your posts and such. Yes, thank you. Excellent. Okay, good, guys. Any more questions before Manpreet and I sign off? It's always an honor to join you guys. Like I said, Integrated's not like, it's there for everyone. You needn't worry if you can make every session or not. And yeah, Manpreet's getting quite popular, so she may have to resort to calls like I do, join calls. So her following is growing super fast. Oh, good, thank you. But Harun, is Mbaabu your first or last name? That's what I most want to be good about.
Harun is the first name.
Okay, thank you, Harun.
Yeah.
Now I know. Hey, any more questions, my family? Our family.
So I should take up that job? That I anyways do, so you can connect with me anytime on Integrated MLAI Slack and LinkedIn. Always welcome to help.
Yeah, this way. Oh, go ahead, Manpreet.
I mean, I try my best, but then I'm also new into all of this. So when I know that somebody is more better than me, I'll connect you all with that person at the moment.
So that's a good point. And the best way, I'd say Manpreet and I are now on our Slack work group for Integrated more than we are on LinkedIn, because we are starting to, I'm almost getting so many messages on LinkedIn I can't answer them all. I hope I'll always be able to answer them all. But please, we welcome you to our Slack channel. What are examples of ML projects for beginners? The practice data sets for both scikit-learn and Kaggle are great starting points, but I would say the easier ones are the toy data sets on scikit-learn. And then I love Moez, who came up with Carrot. I support it. I understand what it does. I've never used it. I've just never needed to yet. But someday I hope to try it out in detail, like on a Kaggle project or something. But even right now, I'm just advising our family members in Integrated how to do Kaggle, but because it's a fundamental machine learning process. Okay, I apologize. I do need to go because I have another scheduled call. Guys, always an honor to be with you, and I look forward to hearing from you in our family chat on Slack. God bless.
Thank you. Thank you so much, Tom. Thank you for joining in, for making this session amazing. It's our last session of the day here. I'm not sure what time it is on your end, but it's at night here. Yeah, so thank you for making our day a success. We really appreciate, we enjoyed the session. Thank you, Manpreet, for joining with us. You've been of great help. Thank you so much. I'm sure we'll invite you again and again and again. Thank you.
Yeah, but we hope that next time we come, we both are as the audience and someone from the community is speaking next time.
Yes, definitely. Yes.
Excellent. Goodbye, everybody. Thank you, Mabel. Thank you,
welcome.
Harun.
Thank you.
Thanks, everyone.
Thank you. Thank you so much. And okay, you are free to leave, but those who are asking how to join the community, you can follow us on Data Science East Africa on Twitter. You can text Harun. He's shared his number there. Then we also wanted to communicate for those of us in Kenya. We have communities for campuses. If you're not aware, you can, the Twitter handle, you can DM Harun there. He'll answer and maybe guide you. We have various data science communities. Thank you for everyone who joined during the entire day. We have other sessions tomorrow morning. We have one at 11, another at 3, and another one tomorrow at 8 p.m. So thank you so much for joining. We appreciate. Yes, our DMs are open. Yeah, you are free to leave. Thank you.